Hi, I'm Szilvia. I am a PhD student here at Lund University. I study neuroscience, and yeah, we don't have too much time, so let's get started. So I will be talking about how we can represent the brain as a vector field, and then how Bayesian methods could be applied in this context. So first I will be setting the scene for today's talk. Then I will introduce the concept of the Bayesian brain in a general scope. And afterwards, I will start from the basics and work our way up to the simulated experiment with which I want to showcase how exactly a Bayesian brain could theoretically or practically be implemented. So first off, who are we? We are from the neural basis of sensory motor control group at the Department of Experimental Medical Science. So basically where we have lunch, but not exactly in that room. So, and we mainly work with neural recording data. So previous talk was about applying Bayesian methods to clinical data. Now we will look at preclinical data. And these neural recordings are just the electrical activity inside the brain. And we want to we try to produce mechanistic explanations in a bottom-up manner to explain the observations that we find within our gathered data. So today I want to answer these two questions. So how can a Bayesian brain be implemented with the system level understanding? And how can it be interpreted? So first, let's talk about what the Bayesian brain could mean. The general idea is that the brain works as an inference machine, so it incorporates prior evidence to make predictions and then updates its expectation. There is no agreed upon definition in the literature. So Peugeot and his group in their 2004 paper, who are one of the first ones to use this term, states that the brain represents sensory information probabilistically in the form of probability distributions. Then a little later, Kristen in their paper say that we try to infer the causes of our sensations based on a generative model of the world. So these are both great things, but where are the Bayesian computations? So besides the fact that there is no agreed upon definition, we find other problems as well. First off, that the formulations that we find are merely theoretical, and there is no empirical evidence that backs up their claims. Then the response that a stimulus elicits depends on many more factors than just the stimulus itself. So these additional variables in this simple equation V could easily render the generative model infeasible to invert. Then the next issue would be, how do we define what a given response is? So how do we isolate it? Considering that brain activity in the brain itself is highly dynamic and highly recurrent, this is not an easy thing to do. And then finally, for this hypothesis to work, the brain must already know its possible set of stimuli and the generative model for each of them, which is again, it's going to be difficult to implement. But anyway, let's see how this can be done. So we will start off with neurons, the basic building blocks of our system. Neurons are electrically excitable cells within our nervous system that are used for information propagation. So a neuron consists of three main components: the soma, the dendrites, and the axon. the dendrites are responsible for collecting the incoming signals from other neurons. And then via the axon, the single signal gets propagated. And then the individual neurons are connected to each other via synapses. And this structure will define the direction of the signal. So this is one directional. And so in this figure, I only show two neurons, but I want to emphasize that that both the incoming and the outgoing number of connections can go to multiple neurons. So it's a many-to-many mapping. Now, if we take a lot of these neurons into consideration, then the connections between them, the connectivity and the communication will define a graph. In this graph, you can see the nodes as being the individual neurons and the edges as being the synapses. And with this formulation, we end up with a graph that is directed. In this case, I did not draw that, but imagine that it is directed and highly recursive. So it can and it does have many cycles. Then within a neuron, we have this summa in function, which is what is collecting the activity that is propagated to the neuron. And this is what we will call the neuron's activity level. And we say that it will be bounded between 0 and 1, where 0 is the neuron death and 1 would be saturation. So that is what would happen during an epileptic episode, for example. So it gets overstimulated. Yeah. So now let's go a step further. Now we have built up from the neurons to a graph, and then this graph will get transformed into a vector field. So how is this possible? Two supposedly have nothing to do with each other. But for the sake of this visualization, let's take a 3-neuronal network into account. So I can draw the vector field. The underlying vector field's dimensionality will depend on the number of neurons. So each axis in the vector field state space will depict a single neuron. And the values that the axis takes are the activities levels of the neurons. So this means that each axis is bounded between 0 and 1. And then within this state space, each point will define an activity level configuration, which means that, for example, if we take the point 04, 06, 08, that is when neuron 0 has an activity of 0.4, neuron 1 0.6, and neuron 2 0.8, and so on. Then the previously defined summa in function will define the transition from one point to the next. So this means that after one time step, where would we end up if we start at an arbitrary point? But if we model this transition for a large number, or maybe all of the possible points in the state space, then we'll end up with something that looks like this. So it's a vector field. Anyway, someone understood that. Yeah, so we end up with a vector field. Then if we take an arbitrary point and we follow the flow of this vector field, we end up with a trajectory. Yeah, so right now we're just looking at the 3-dimensional case, but this can be extended to any number of neurons, which is good since we have more than 3 neurons in our brains, hopefully. And this is just a simulation of 3 different initial states that are following the vector field from before. So these are 3 different trajectories. Okay, now let's get to the experiment. So how can we implement the Bayesian brain? So over the course of evolution, to survive, we have been able to adequately respond to external sensory stimuli. And in this experiment, this is what we want to figure out. So how does this happen? In the experiment, we will start with a biologically inspired neuronal network. Now we are moving out of the dimensional case and to 18 dimensions. So unfortunately, I'm not able to show the underlying vector field. But so this 18 neuronal network we will think is a brain, and it is trained. So what does this mean? It means that the underlying vector field will have a meaningful structure. And this structure is correlated to the stimuli response mapping in a way. And that is what we want to infer. So that's what we're interested in. So the experimental procedure is done in such a way that we first provide an external stimulus to the subject, which in this case is the 18 neuron network. Then we will be measuring the neuron activity levels for each of them. And then we will be observing the response that was elicited by the stimulus. And we will be repeating this process a number of times, and that will be our data set. So how does this map to vector field terminology? The external stimulus will be an initial state in the vector field, so an activity level configuration. Then the measured neuron activity levels will be what I showed, that it will be a trajectory through the state space. And then finally, the response will be, it is really up to us. It's a high-level interpreted mapping from what we see as a response and what behavior we map it to. And so in the experiment, for simplicity, we use a deterministic vector field, which means that the goal of mapping the vector field to the stimulus can be reduced to mapping the, so the goal of mapping the trajectory to the behavior can be reduced to mapping the stimulus to the behavior, since every stimulus will uniquely determine a trajectory. So the idea with the Bayesian brain is that this underlying mapping between stimulus and behavior is done in a probabilistic way. So there's some underlying distribution there. So this can be thought of as a soft clustering of the high dimensional vector field. Anyone? Yeah. So let's assume that this underlying unknown distribution is a multivariate Gaussian mixture model, where the number of components will be the behaviors that we as experimenters will distinguish between. So that is up to us, more or less. And then the multivariateness comes from the high dimensionality, which is coming from the number of neurons. So all of the wall space characters or variables in the equation will have 18 dimensions, or a sigma will be an 18-dimensional square matrix. And in the experiment, we will be modifying the mixing coefficient, which is essentially a weighting of the mixture components, or in simpler terms, which behaviors are we more likely to choose. And as an example, if we take just a two-neuron network with two mixture components, we might end up with something that looks like this. So the points will be the input, the stimuli, and these ovals are the underlying mean and covariances of this mixture model. So here we have the two behaviors. Yeah, so to generate our simulated data set, we will just do a sampling from the multivariate Gaussian mixture model, which is, again, 18-dimensional. So we can use a dimensionality reduction method called PCA, and we will map it to its two-dimensional equivalent. So here we start off with the 18 neural network case, and we manually set the number of behaviors to be 3. So that is reflected in the low dimensional case as well. And then in the next step, so here we just run the inference via a pre-implemented algorithm. In the upper right corner, we have the distributions that we want to obtain. So as I mentioned, the priors that we set are over the distribution for the behaviors. So by setting this, we not only say which behaviors are more likely to be chosen than others, but we are implicitly defining the number of behaviors as well. So how many Ks there can be. But as I mentioned in the first part of the talk, that this exactly is the problem, that defining the number of responses that we get is not so straightforward. So maybe as experimenters, we would want to overestimate the number of behaviors we can get. So let's say that we set K to be 6 instead of 3, but reality this can be a much larger number. So then we run the inference on 2 different priors. How I chose them, the matter everyone else has talked about choosing them. So we will believe them. And we see that we get 2 different posteriors, and we can ask ourselves which ones seem to be, or which one seems to be the correct one. And I hope everyone says this one. But if not, there's again the reminder of what we are looking for. In this case, it's very easy for us to evaluate which of the results is better, since we are the ones that generated the data, but in reality, we don't have true labels, so evaluating the goodness of fit of our model is not that simple. So the posterior of prior 1 could just as easily be correct as a prior 2, but we have no way to verify it, and that is then another problem or another issue that I mentioned at the beginning. So to summarize, we can answer the two questions at the beginning of the presentation. So how can the Bayesian brain be implemented? Well, we showed that with these Bayesian methods could be implemented in a vector field representation of this simulated network, but along the way we have applied simplification upon simplification and assumption after assumption. And the rest that I didn't even touch upon. But you might be wondering, why would we even want to do this if it was all this trouble? Well, if we have the underlying distribution, and as I mentioned, we are measuring the neuron activities, which are trajectories in this vector field, then with the combination of the two, we will be able to reconstruct the underlying vector field, which then is determined by the original connectivity. So if we have the vector field, then we can reverse engineer and get back the chromosome. So essentially reconstruct the brain. It should be nice. We're not saying it. And then secondly, how can this be interpreted? So the prior that we were setting again is we are influencing how certain behaviors get chosen. And in a high-level interpretation, this could mean, okay, so we have a subject, how are they going to choose certain actions over other actions? But in reality, this is based upon our previous experiences, our history, and our habits, and that is incredibly hard to model. So, thank you for